announcements before we start. So so you know, as you know, as you may have noticed, you know, this colloquium this semester has developed a bit of a theme to it in the sense that it's many of the talks have been aimed at getting more of a dialogue between experiment and theory. And so we're going to be continuing that tradition today, actually in an even more intense way. Next week is Thanksgiving, so there'll be no colloquium. And then the week after that, Robert Huang from Caltech will talk about making predictions in a quantum world. So that'll be our last colloquium for this semester, and then we'll resume in January after that. Okay, so so for today's talk, you know, as I said, it's actually you know, in this theme of a dialogue between theory and experiment, but in fact it's a dialogue between theory and experiment within the same talk. So it's actually going to be, you know, it's really great to have Andru Gheorghiu and Daiwei here, who are going to be tag teaming today's colloquium. So Andru will describe the theoretical work, and Daiwei will describe the experiment that they recently concluded based on that work. So let me just introduce them. Alexandru Gheorghiu, he's currently a junior fellow at ETH Zürich. He got his PhD from University of Edinburgh, and then he did a postdoc at Caltech. He has done some very beautiful work on you know, protocols for verifying quantumness or quantum clients with classical verifiers. Daiwei Zhu is, he just finished his PhD at University of Maryland, working on Trapdoor quantum computers and algorithms targeting near-term quantum devices. He's now a senior application scientist at IonQ, and his research interests include not just that, but quantum algorithms, hardware-based quantum algorithm optimization, and the verification and characterization of quantum devices. So looking forward to your talk. So Andru, please.
Great. Thank you so much. So just to double check, can everyone, or can someone at least hear me okay?
Yeah.
Mm-hmm. Okay. Okay. Can you also see my cursor when I move it on the screen?
Looks good, Andrew.
Okay, thanks so much. So thank you so much, Umesh, for the very nice introduction. It's a pleasure to be speaking here. So as Umesh said, I'll be talking about this work, which was a very large collaboration involving a number of experimentalists as well as theorists. So I'm not going to name all of them. You can see them here. And I just want to say that I'm grateful to all of them. I think this was, you know, a really nice collaboration overall. Okay, so we live in quite exciting times from the perspective of someone working on quantum computing, because just recently we've kind of seen some of the first demonstrations of what's known as quantum advantage. So the idea of performing a task efficiently on a quantum device that we believe is intractable for classical computers to do. So the first such claim was from Google in 2019, and since then there have been others from the University of Science and Technology in China. And just at a kind of high level, what all of these experiments have generally done is to perform a random quantum circuit on a device and then measure from the output of that circuit. And we have strong theoretical evidence that this task is hard to do for classical computers, to sample from that distribution. But quantumly, it's something that we can do efficiently, though I don't want to say that it's easy because it required a lot of technological breakthroughs to get here. So these demonstrations of quantum advantage are, they've been done with existing devices, which is really nice. And it really is due to this random circuit sampling problem, which kind of lends itself to be implemented on the devices that we currently have. And as I said, there's also good theoretical support for why this problem is classically intractable. And also there's also some evidence that even if you have noise in your system, it's still intractable to sample from that distribution. So even if you sample from something close to that distribution, that should still be intractable. But there are also some disadvantages with this approach. And I would say the main one in relation to this work is that verifying the results of your sampling task is classically intractable. So the problem is that you're not directly verifying that you're sampling from this distribution. And so what you do is you perform some sort of statistical test on the samples that you received. And the specific tests that were performed are computing the linear cross entropy of these samples. And this is something that requires exponential time to do classically. So it doesn't seem like this would scale up. And another more subtle problem is that while we believe that sampling from the distribution is hard, we don't know whether that also implies that spoofing this linear cross entropy test is also hard. So there seems to be a gap there in relating the hardness of these two things. So this kind of motivates and begs the question, is there some other way in which we could do quantum advantage to address these two issues? So this leads to the concept of interactive proofs of quantumness, which were introduced in this seminal paper by Gheorghiu, Cristiano, Mahadev, Azurani, and Vidic in 2018. And the general idea is to have a protocol or a test, an interactive test between a classical computer and a quantum computer, or an ostensibly quantum computer. And the point is that the quantum computer should be able to pass the test, but no classical computer should be able to, assuming the hardness of some cryptographic task. And I hope this will become clear throughout the talk. So we have this classical computer, which I'll refer to as the verifier, that is trying to test this ostensibly quantum computer to see if indeed it can pass the tests in this protocol. And the general structure of such a protocol is something where first you have some sort of setup phase, so an initial message from the verifier to the quantum computer that kind of sets up the cryptography that's used in the protocol. Then the prover will perform something that's called a commitment step. And then there's a challenge that the verifier issues relative to this commitment, and then it checks the response of the quantum device from this challenge. And what we'd like to achieve in this protocol is, if you're actually talking to a quantum computer, the verifier should accept with very high probability. Whereas if you're talking to just some other classical computer, then she should reject with very high probability. And the inability of a classical party to pass this test should be based on this cryptographic assumption that kind of underlies it. So as I said, these two parties are the verifier and the prover. And from now on, whenever I say efficient, I will mean that it can be done in polynomial time. So there's a polynomial time algorithm, or like the number of rounds, or sorry, the amount of communication is polynomial, the number of operations is polynomial, and the size of some input. And also when I say intractable, I mean there's no polynomial time algorithm. And as I said, this intractability will come from some sort of cryptographic assumption. So let's see what cryptography we would have to use to design such a protocol. So in the Gheorghiu et al. Result, they relied on this notion from cryptography called the Trapdoor claw-free function. So this is a mathematical function that satisfies four properties. First, it should be efficient to evaluate. So given any input, it's efficient to compute an evaluation of the function. The function should be 2 to 1, meaning that for every point in the image of the function, for every evaluation of the function, there are exactly 2 inputs that lead to that evaluation. So 2 pre-images, we would call them. Then this is where the intractability comes in. It should be intractable to find the triplet of an image of the function as well as the 2 pre-images associated to this image, given as input a description of this function. And lastly, the trapdoor refers to the existence of some sort of secret information, T, the trapdoor, which if you have this trapdoor, then there is an efficient way to invert the function. So there's some algorithm that, given the trapdoor and an image of the function, it can recover the two pre-images in polynomial time. So just a bit pictorially, as I said, you have this function which should be efficient to evaluate. So you're mapping from some input to some output, and this should be done in polynomial time. And for every input, there's also a sibling. So there are always two pre-images to any given evaluation of the function. And the claw-free property says that given this function, it should be intractable to find any such triangle, so a triplet of two pre-images and the image associated to them. And of course, there are many such pairs. And in general, the image of the function will be smaller than this output domain because it's a 2-to-1 function. Okay, so having this notion of this TCF, this trapdoor claw-free function, let's see how one would design a protocol that leverages this to test for quantumness. So in the setup phase of the protocol, the verifier will generate this trapdoor claw-free function together with the trapdoor. It will send the description of the function to the prover, but it keeps the trapdoor to herself. So then what it's going to ask the prover is to give back an evaluation of this function. So the commitment, if you like, of the prover is that it evaluated the function and returned a particular evaluation of it. And now the challenge that the verifier is going to issue is actually one of two possible challenges, which she picks with equal probability, so with probability 1/2. So one challenge is to request a pre-image of this image that was previously reported. So just an x such that f of x is equal to y. And of course, the verifier can check this efficiently by evaluating the function. Or the other test is a so-called equation. So an equation is a string D such that the inner product of D with the XOR of the two pre-images for this y is equal to 0. So it's some sort of string that has a special relationship to the two pre-images. And intuitively, this kind of hints at that claw-free property that we think is, that we assume is intractable. But I'll talk more about that in a second. So this is the protocol. So the verifier will issue one of these two challenges upon receiving the image. And as I said, in the pre-image test, she can just evaluate the X it receives to check if it's a valid pre-image. In the equation test, she needs to use the trapdoor to compute the two pre-images for this Y and then evaluate this equation with the reported D from the verifier. And if either of these two tests is passed, then, or I should say, if both of these tests are passed, then we say that the prover has succeeded in this protocol, and otherwise the verifier will reject. So let's see now why a quantum prover can succeed in this protocol. And I think this will also give you some intuition about how this equation test is, because I think that's the more counterintuitive bit of the protocol. So on a quantum computer, what we would do is we would initialize two registers, one in which we store the inputs of the function and one in which we store the outputs. And what we want is to evaluate the function in superposition. So first we create a superposition over all inputs. Then we evaluate the function coherently on that superposition. And then to obtain the evaluation of the function, we just measure the image register. And if you're familiar with Simon's algorithm, it's very similar there, where the pre-image register is going to collapse to a superposition of the two pre-images compatible with this Y. And then this Y is sent to the verifier. So then the verifier can request a pre-image, in which case the prover would just measure this pre-image register in the computational basis and get back one of the two pre-images. And in the other case, we can see that what the prover would have to do is first apply a Hadamard operation to this register and then measure in the computational basis. And again, just like in Simon's algorithm, it's not difficult to show that such a measurement of this state will yield a string D that in binary inner product with the XOR of these two pre-images is equal to 0. So in this way, we have a quantum strategy that can always succeed in this protocol. So what about classical strategies? How do we know that there isn't an efficient classical strategy for such a protocol? So let's try to sketch an argument for why it shouldn't be possible for a polynomial time classical prover to succeed. So in this case, the prover we assume is classical, and we assume that it can answer the challenges correctly. And so if we were to run the protocol, so let's say we run the protocol with this classical prover and perform the pre-image test, we get back a valid pre-image because we assume the prover can always succeed. But now, because this prover is classical, all of its operations consist of some deterministic set of gates that are applied to a set of input bits. And these bits can also contain randomness. So the prover can also pick some random bits as part of its input on which it evaluates the circuit. But nevertheless, if we fix this randomness, whatever it used in the protocol, we can then just rewind, we can uncompute what the prover did to just after the point where it reported the image of the function. And then we can run the other challenge with this prover, so the equation challenge. And by our assumption, we know that the prover must succeed in both of these. And so this means that with this rewinding operation, we can essentially construct a polynomial time algorithm that produces an image of the function, a pre-image, as well as a valid equation in both of those pre-images. So now you might ask, so does this contradict the ability to find claws or pre-images for this trapdoor claw-free function? And in fact, it's not clear that it does, because the claw-free property says that it's hard to find both pre-images together with the image, whereas here we're finding the image, a pre-image, and some sort of bit of the other pre-image, which we could obtain from the string D and the other pre-image that we have. So the TCFs that I've defined so far are actually not strong enough to guarantee that it's hard to also find a valid equation. And this motivates us to introduce a stronger notion of TCF, which I'll just call strong TCF. And this is essentially the same TCF as before, except we change the claw-free property to this adaptive hardcore bit property. And this just says that instead of it being hard to find an image and the two pre-images, it should be hard to find an image, one of the two pre-images, as well as the string D that satisfies an equation in both pre-images. So it's kind of like saying, if you have one of the pre-images, then you shouldn't know even a single bit of the other pre-image. So it's a much stronger property than the claw-free property of regular TCFs. So if we were to use these strong TCFs in the protocol instead of TCFs, then everything would work. So the previously mentioned classical hardness argument would work. It would give us a contradiction with this adaptive hardcore bit property. So as long as we can construct these functions from standard cryptographic assumptions, then we have that there's no efficient classical strategy that can succeed in this protocol unless you break that cryptographic assumption on which these functions are based. So in fact, an even stronger fact is true about the classical hardness of these protocols. Namely, if you denote the success probabilities in these two tests as P sub pre and P sub EQ for pre-image and equation tests respectively, what you can show using a slightly modified variant of the rewinding argument is that for classical provers, this inequality needs to be satisfied in the two probabilities. So not only can a classical prover not succeed perfectly, but it can't even achieve success probabilities that would violate this inequality. Whereas quantumly, we know that you can succeed perfectly in both tests, so this value is equal to 3. So there's this gap between the best classical strategy and the best quantum strategy. And this means that if we were to perform this protocol, as long as we're with statistical significance above this 2 value, which is the classical threshold, then we can be confident that we have quantum advantage, as long as the cryptographic assumption was not broken in the protocol. Okay, so this explains how we can design these proofs of quantumness based on these strong trapdoor claw-free functions. But of course, it begs the question, can we do it with just trapdoor claw-free functions? So without this adaptive hardcore bit condition. So in answering that, we first need to understand what the adaptive stands for in adaptive hardcore bit. So it refers to the fact that the prover can choose the string D that satisfies this equation. So the prover in some sense has a lot of leeway here, in that it's free to choose any such D that satisfies an equation in the two pre-images. rather than say maybe this D being fixed in advance or being chosen randomly or something like that. So to kind of get around this obstacle and get a protocol that works even with TCFs, it was shown in this recent work by Greg Meyer, Sunwon Choi, Umesh Vazirani, and Norman Yao, that what you can do is you can have the verifier try to force a specific equation onto the prover in some sense. And I hope this will become clear in the next slide. And this leads to what's called a computational bell test protocol. So what is this protocol? So now recall that we have this TCF, we don't have the adaptive hardcore bit property. So the protocol is actually almost the same as the previous one. So we still start by sending the function, we get back an evaluation of the function. And there's still going to be a pre-image test, which is the same as in the previous protocol. But now, instead of having the regular equation test, we're going to do something a bit different. So if we're at this point in the protocol where the prover, the honest prover, has reported the image, then it should have this superposition state of the two pre-images. And what's going to happen now is the verifier is going to pick a random string of the same length as these two pre-images and send it to the prover. And the prover is instructed to create this state. So to take this string R and compute coherently the inner product of R with the two pre-images that are in superposition here, and then put that result in a new register, so in a new qubit. So then what the verifier will do is she will ask again for a string D, just like in the equation test of the previous protocol. And this is obtained by doing a Hadamard measurement on this second register that holds the pre-image and measuring it. So exactly like in the previous protocol. And what we can see now is that the state of this first qubit, if you were to do this measurement, becomes this one. So you have a superposition of these two components that relate to this R string, and the phase is given by this D string that comes from Hadamard measuring the second register. So what's interesting about this qubit is that it's a BB84 state. So it's either 0, 1, plus or minus, because when this R inner product with X0 is equal to R inner product X1, then you just have a 0 or a 1 state, so a computational basis state. And if they're different, then you have a superposition state where the relative phase is given by the D string that was reported by the prover. So the idea now is that this you can think of the state before the measurement as a sort of entangled state, like a maximally entangled state between these two registers, and that this the D string was the result of measuring half of this entangled state. And now the verifier will instruct the prover to measure this other qubit that we're left with in the same of the two bases that you would encounter in a normal bell test. So these two rotated bases. And once the prover performs this measurement and sends back the outcome, the verifier can use all of the information that it has. So it can use the trapdoor as well as the string R and D to figure out what this qubit was that the prover was supposed to have at this point in the protocol. And from that, she can also determine what the most likely outcome with respect to this measurement would be, because the outcome will be biased towards one of the two elements that you have in your basis. And it's not too difficult to see that just like in the regular bell test, quantumly you would succeed with probability 85%. So your bias is kind of 85% towards the most likely outcome. So what is achieved in this setup is that a quantum prover can succeed in this modified equation test with 85% probability, whereas classically you would have, just like in the standard bell test, 3/4 probability of succeeding. So the same kind of gap between quantum and classical will arise here. So again, if we denote the two probabilities for the two types of tests, we find that the classical threshold here is given by this inequality. And this is, again, just like in the standard bell test, it's because classically you can think of this as being at most 3/4, whereas in the pre-image test, you might succeed with probability 1. And so this gives you a maximal value of 4. Whereas quantumly, we saw that you could succeed with 4.41 violation of this linear constraint on the probabilities. So again, this gives us a way to test for quantum advantage. Okay, so what Daiwei is going to tell you about is how we actually implemented both of these protocols. And before getting to that, I need to just mention how we actually constructed the two types of functions that we would use in the protocol. So first, the strong trapdoor claw-free function, which is constructed based on the learning with errors problem. And then for the second protocol, this bell test protocol, the trapdoor claw-free function, because it doesn't have this strong adaptive hardcore bit property, we actually know how to construct them from multiple assumptions. And for our purposes, we used factoring as the underlying hardness assumption, so the hardness of being able to factor. So I'll assume people are familiar with factoring, so I'll just quickly mention what learning with errors is in case that is unfamiliar. So learning with errors is basically the problem of solving an approximate system of linear equations over some finite rings, so say over modulo Q. So you're given a matrix A and some vector, which is really close to something of the form A times S. So it's not exactly A times S. If it was A times S, you would be asked to just solve a linear system of equations. But instead of being given that, you're given a noisy version of this A plus S. So you have some sort of error vector, as it's called, that is applied to this AS. And this vector has very small norms, so all of its components are very tiny. And so what you know is that there's some approximate linear equation that is satisfied, and the goal is to find this secret vector S, so to solve this approximate linear equation system. So in the example I have here, the secret vector is just 1, 0, because 1 just selects the first column, which is 2, 0, 1, 1, and that is the one that is, say, closest to this result of 3, 0, 1, 1 that we have. And the reason I picked this specific example is because this was one of the instances of STCF that we constructed and actually performed with the ion trap quantum computer. Okay, so that was the hardness assumption that underlies it, but how do we actually construct the functions? So one type of strong trapdoor claw-free function that you can construct from LWE is the following. So it takes two inputs, a bit B, so it's either 0 or 1, or a vector X, which is of n components modulo Q. And what it does is it just multiplies A with X. So you're given this LWE instance, you're given the matrix A and some sort of vector AS plus E. And what you do is you compute A times X, and then condition on the value of B, you then add this LWE vector or not. So if B is 0, you don't add it. If B is 1, you do add it. And then you perform what's called a rounding operation on the result. So this rounding operation just means taking the most significant log P components of your result. So if P is equal to 2, it just means taking the most significant bit of your result. So from each component in this output vector that you have here, you just take the most significant bit of each component. And that's the result of your function. And I won't go into the why this satisfies all the properties of a strong trapdoor claw-free function, but just to say where the claws of this function are. So they're going to be at the points 0x and 1x minus s. And it kind of follows from the fact that 0x is just the rounded version of ax, and 1x minus s is the rounded version of ax plus e. But if this e is very small, as we assumed it is, then this just rounds to the same thing as ax, because the high order bits of the output are unlikely to be affected by this small vector e. So that's how we get the clause. And you can see how finding clause for this relates to finding the secret S. And of course, this adaptive hardcore bit property, which is the one we really care about here, is also satisfied, but that is not at all obvious from this description. Okay, so that was the STCF. Now for the TCF. So here there are many ways in which we can construct it, but the one that was used here is the so-called Robbins function, which is based on factoring. So here you take some composite integer n, which is the product of two large primes, and your function is just x squared mod n. So here again, let me just, I won't go into why this is a TCF, but intuitively the clause are at the points where if you get some output y, then x0 and x1 form a claw if x0 squared is congruent to y modulo p, and x1 squared is congruent to q modulo p. And so if you know the factorization of this n, then you also know where the claws are. So this is kind of the trapdoor aspect of the function as well. Okay, so we have these functions. So let's see how we would implement the quantum strategy that we actually ran on the quantum computer. So the goal is to create this superposition over evaluations of the function, as I mentioned before. And we can see that if we were to break this down in terms of qubits, this b is 1 qubit, x, because has n components and they're all modulo q, has n log q qubits. And then this f, so you can see that the output of this function is an m component vector. And we're doing this rounding operation. So you have m log q bits in your output, and then this leads to that same number of qubits. And in fact, for the implementation, we will need an extra register of log q qubits to do some, to essentially do the computations required to evaluate this function. So the parameters we used when considering instances of this problem to design these functions were 4x2 matrices that were modulo 4, so q was 4, and p is equal to 2, which means we were rounding to the most significant bit. And you'll see the specific instances in Daiwei's part of the talk. So at a high level, the circuit looks something like this. So you start by putting all of your qubits into superposition. And then what you're going to do is compute inner products between each row of the matrix and your input vector x, as well as adding this components of this other vector. And you're going to do all of that in phase. So these V unitaries just consist of 2 qubit phase rotation gates. So then you need to extract the result in the computational basis because you need to report an image to the verifier. So you need to do an inverse QFT, which is only on log q qubits because that's the size of the output here. You take the most significant bit, so that's the rounding operation. And then unfortunately, you need to uncompute because we want to reuse this register for the next component. So this diagram here is repeated for each of the rows in the matrix A. And so you can see then that the overall gate count will be dominated by the size of this matrix A. So it's something like mn log q. And in our case, using various optimizations that maybe we could talk about later if there are questions, we were able to bring this gate count to under 150 gates. And we really benefited from the all-to-all connectivity of the ion trap in order to do this. So the ability to be able to do long-range gates between any of these 2 qubits. So as I said, there were several optimizations that went into this, but maybe I could talk about that if there are questions. So then moving on to the other function, the x squared mod n one. So here it will be useful to denote as little n the size in binary of this modulus n. So again, we want to create an equal superposition of evaluations of the function. And in this case, the number of qubits that we will need will be 2n plus 1. So it's 2n because you can see that each one of these registers would normally have n qubits. And the plus 1 is for that extra qubit that we use in the computational Bell test. So the one that is measured in that rotated basis. So here, the only parameter you can vary is the size of this n, the number to be, the number on which we base the hardness on being on the factoring of this number. And the instances we chose were 8, 15, 16, and 21. Now you might be a bit puzzled about 8 and 16 because they're not products of 2 primes. But again, there are various tricks that you can do to get around this so that you can make these cases work as well. And again, I can maybe talk about that if there are questions.
Andru, could you, I think we are slightly at the edge of the time, so if you can sort of
in
a couple of minutes or so.
Yes, sure, sorry. I'm almost done anyway. So the circuit structure is kind of similar to the other case. You evaluate the function in superposition, in phase, and then you do a QFT to convert it to the computational basis. And then you have the parts for doing this computational Bell test that I measured. So the gate count here is cubic, but again, with various optimizations, it's under 150 gates. And there are various trade-offs between qubit number and gate count that you can achieve. And just one point that I'd like to mention here is that even though we're relying on the hardness of factoring here, this protocol, or at least this circuit, is much simpler to implement, and it's a much smaller circuit than, say, performing Shor's algorithm. So there's no phase estimation being done here or anything of the sort. Okay, so to kind of wrap up, we have these protocols that are based on standard cryptographic assumptions. And as we saw, the number of rounds of interaction kind of depends on whether you use the strong trapdoor claw-free function or the regular one. So you have 2 rounds of interaction versus 3 in the 2 cases. And we also saw like what the circuits looked like, and we really benefited from the all-to-all connectivity in order to fit everything within the qubit and gate budget that we had available to doing this. And one nice thing about the STCF-based protocol is that you could also use it to generate certifiable randomness. So that's like a very nice spin-off application that comes as a result of this. So, in the future, we'd obviously like to be able to improve on these constructions, so come up with more efficient constructions, maybe have more noise robustness, and reduce whatever, like the number of interactions or the gate count and so on, to make them more feasible for near-term devices. So with that, I'll now let Daiwei tell you about the actual experiment that was performed.
Thanks.
So maybe I'll stop sharing my slides. Yeah, and sorry for overrunning.
Thanks, Andru. While Daiwei sets up, is there a question that?
So Andru,
yep.
So just to get an idea, so what's the size of more or less, in the 2 cases, M and N, that you need to set for having a classically hard instance?
Right. So I should have said that these are proofs of proofs of principle demonstrations, because of course the instances are so small that you can solve them classically efficiently. So probably M and N would be on the order of thousands or hundreds, something like that.
Is there a big difference in the two, the 2 different tests for how many qubits you would need at scale?
So I think they might be quite comparable. So it's a bit hard to compare because in the factoring case, there are sub-exponential classical algorithms for factoring, whereas in the LWE case, the best algorithms take exponential time. And so the scaling will be different in the 2 cases. So you might need a very large N, say, in the factoring case, whereas the LWE instance might be comparatively smaller. But I think that to demonstrate quantum advantage in both cases, you would probably need thousands of qubits to do it. Like maybe 2,000 or 2,000 was the estimate we had for quantum advantage, 2,000 qubits.
Okay, thanks. Daiwei, are you?
Yeah. So can everyone hear me? Yeah. Yes, the screen sharing is working. So yeah, all good. Okay. So thanks, Andrew, for the excellent theory introduction. I will now continue presenting the experiment part of our work. What you are looking at here is a high optical access trap version 2.0 developed by the Sandia National Lab. It is essentially the heart of our ion trap quantum computer. So I will first cover the hardware or the construction of our quantum computer, and then continue on to how we actually use it to implement the experiment, the protocols. So our qubits are made of a chain of ytterbium-171 ion trapped with this kind of surface trap. This type of surface trap particularly have many microfabricated electrodes along this region that can each be independently adjusted. So this provides us with very great control over the configuration of the ion chain. We can deterministically load desired number of ions, as you see here, and also perform split, merge, and shuttle of the ion chain. This capability is crucial to the implementation of the interactive protocols we're going to talk about here. So let's further zoom into the internal state of each ion. So each ytterbium-171 ion provides us one physical qubit in the form of a pair of states in the hyperfine split S ground level. This split is insensitive to magnetic field to the first order, which gave our qubits pretty long coherence time. This plot on the right shows the measured coherence time T2 of different qubits in the configuration we used for the experiment. It goes to around 4 seconds. Another way to put it is, in theory, this 4 seconds enable us to do about 20,000 2-qubit gates. But this T2 is only limited by technical noise and experimental imperfection in our case. With some careful engineering, T2 of larger than 1 hour has been demonstrated experimentally by Ki-Wang Kim's group at Tsinghua University. So the pair of states in the hyperfine splitting are defined as computational 0 and computational 1. We use state-dependent fluorescence to distinguish them. To be more specific, we illuminate this 370 nanometer light onto the ion, and only the computational 1 state would resonate with this 370 light and scatter photon. So in another word, we basically look at if the ion shine to determine it's 0 or 1. And to realize individual readout, we use a fiber array to guide the photons we collected from each individual ions into a PMT array to do individual readout. So we use a high power 355 pulse laser to drive what's known as Raman transition between the two computational 0 and the computational 1 state. The control in the phase and amplitude of the driving laser provide us with all the degrees of freedom that we would need to realize arbitrary single qubit rotation. To complete the universal gate set, we use Ising gate. Here is the Ising gate, which is mediated by the collective motion of ions. So because of the Coulomb interaction among all the ions, they oscillate collectively, forming different motional modes as shown here. By matching the detuning of our laser to these frequencies of motional modes, we couple the internal state, the qubit state, to this motional modes. So this shared motional modes can thus be used as quantum bus to mediate 2-qubit gates. So this grants us all-to-all connectivity, which turns out to be very convenient for this protocol, this type of algorithm, which means each qubit, as shown here, can directly couple to any other qubits within the chain via the shared motional bus. So putting all the ingredients introduced above together, we can build a quantum computer. Here is some key specs of the quantum computer we used for this project. For the specific configuration we used, it supports up to 13 qubits. And the 2-qubit gates fidelity is around 99%, depending on the specific pair. The single qubit gates fidelity goes to beyond 3.9. Okay, so before we dive into the experimental result and some experimental implementation, let's just review the protocol one more time. Both protocol starts by prover preparing a superposition according to the configuration specified by the verifier. The prover then perform a measurement on the output register and report the result, which is the image, to the verifier. The verifier then requests either a pre-image test or an equation test, as Andru introduced before. So in the case of LWE-based protocol, the equation test basically means measuring the hardcore bit. In the case of the factoring-based protocol, the equation test involves performing the computational bell test. Thus, we would require some extra rounds of interaction. Based on the prover's response and the information obtained using the Trapdoor, the verifier can then decide to whether pass or fail each single run of the protocol. So these are the configurations of the instances of each protocol we used for the experiment. This table shows the 4 instances we used for the LWE-based trapdoor function. And for the factoring-based protocol, as Andrew mentioned before, we also studied the 4 case with n equals 8, 15, 16 to 21. To implement the protocol, we use this 2 type of circuit. In both cases, it involves using a unitary to prepare the superposition and then perform mid-circuit measurement as circled in red here to generate a cloud, which is a superposition between x0 and x1. For the LWE-based protocol, it ends with measurement performed in the requested basis. For the factoring-based protocol, this extra round of gate plus partial measurement, again encircled in red, are implemented to do the effective Bell test. So the partial measurement is necessary here, very crucial for the cryptographic soundness of the interactive protocol. It is also, in general, a crucial component of quantum computation. It is not only necessary for quantum error correction, but would also enable other many different type of algorithms. But it's also very hard to implement. So one aspect of the challenge is shown here. So we normally pack the ion chain pretty tightly together so we can improve, so we can perform the 2-qubit gates fast and accurately. But such configuration is inconvenient to partial measurement because during partial detection, the stray light easily scatter into qubits that we want to keep for the rest of the operation and thus cause decoherence. So to achieve partial measurement, we fully utilize the voltage tunability granted by our surface trap to adopt the split and the shuttle technique as also used by Honeywell and the NIST. As shown here in the figure, we perform the gate in a packed chain. But when we want to perform partial measurement, we split the chain, we split the subset to be measured apart from the subset that we want to keep for the rest of the protocol. And we shuttle the subset we want to keep away from the detection system to minimize the impact of stray light. This video shows the change of the ion chain configuration throughout a split and shuttle operation. So this is the split and shuttle sequence in particular for the LWE-based protocol. The red dashed line indicates the alignment of the ion to the center of the system where quantum operation and detection happens. We first generate the superposition with the whole chain and then split the chain into 2 parts so we can measure the output register W to get the image, but keep the rest of the chain intact and store them for the rest of the protocol. And then, depend on the requested measurement, depending on the requested test by the verifier, we perform the operation, we move the subset that we kept away back to the center of the system and perform the rest of the operation. For the factoring-based protocol, the procedure is similar, except for an extra round, except the extra round of splits and the partial measurement is needed to complete the computational Bell test. So experimentally, how do we characterize the quality of the partial measurement? Or to say, how do we probe the coherence of the qubit throughout the partial detection? Because that's our #1 concern regarding the stray light, regarding the coherence. So the tool we use is classically known as very classic, known as the Ramsey experiment. The Ramsey experiment basically probe the coherence of a qubit by scanning the relative phase between 2 high half paths. The projection of the result of the composite rotation in the z direction depends on the relative phase, and the amplitude of such oscillation directly relates to the coherence. So in this experiment, we basically do a Ramsey experiment, but we insert partial detection in between the two pi-half plots. So we can see how much the coherence is disturbed by the partial detection, or to say how much coherence we can maintain through the partial detection. So as you can see from here, we detected the qubits marked in blue, and the coherence is eliminated because of the partial detection. But for those qubits we kept away from the detection, which are marked in orange, the coherence is well maintained. Another issue for the shuttling and partial detection is the extra phase induced by shuttling. So when the ions are shuttled around, they go through slightly different magnetic field and thus accumulate various extra phases. As you can see here, compared with no shuttling, the Ramsey fringes of some qubits with shuttling offset from the others because of this accumulated phase through shuttling. So to perform the protocol, or to correctly perform this partial measurement, we characterize this phase using this Ramsey experiment and compensate for that by performing extra Z rotation on such qubits after every split and shuttle operation. Okay, so here's the result. We performed the experiment both with actual interaction or delayed measurement. So by delayed measurement, what we mean is that all the measurements are deferred to the end to pretend they're interactively measured, but actually not. So doing this, comparing these two, actually enable us to estimate the error overhead of partial measurement. Much like a Bell test, as Andru emphasized before, each classical prover can pass the verifier's challenge with non-trivial probability. But this probability can be bounded by an asymptotic classical threshold defined on PA and PB. Andru, you used P pre-image and P equation test. But here it just two tests depend on the verifier's request. And this asymptotic bound threshold is ultimately what we use to evaluate the performance of our experiment. Or equivalently, whether a verifier would accept the quantumness of the prover is based on whether they exceed this threshold in this region, classic, or in this region, quantum. For the LWE-based protocol, the asymptotic bound is PA plus 2PB, no greater than 2. For the factoring-based protocol, such bound is PA plus 4PB, no greater than 4. For each configuration and each branch of choices that the verifier could make, we repeat the experiment, the protocol, for 2,000 times to collect the statistics. For all the instances of the LWE protocol, as you can see from here, the quantum prover exceeded the asymptotic bound. For the factoring-based protocol, except for the n equals 21 case, which by far requires the most number of 2-qubit gates, all the other instances pass the threshold. Another way to look at the data is the relative performance shown here, given for each branch of choice the verifier would make in each instances. So this is a definition of the relative performance. It basically shows the percentage advantage of our experiment has against random guess in each of the case. So a completely noisy quantum computer will have zero advantage over random guess, but an ideal quantum computer will reach 1. Comparing the interactive implementation against the delayed measurement, we can see that some of the branches we can see that the different branches are impacted by the partial measurement induced decoherence differently. In particular, for this thickened branch, and also they're squared with a red square, they are robust against such noise, as you see compared with this case. The measurement, the intermediate measurement doesn't really cause much loss. Theoretically, we know this is because such branches do not depend on the phase coherence between x0 and x1. And because the partial measurement implemented in the way we do in our experiment dominantly induce phase error, so those branches naturally are going to yield similar performance, interactive or not. For the factoring-based protocol, another very interesting observation can be made. You can see from here, as my cursor, the pointer is pointing to, is that you can see that the extra arrow from partial detection actually increased the performance of this particular branch. This is because we are effectively performing a bell test. And you know, in a bell test, systematic error can boost up the performance of certain branches, of course, at a larger cost to other branches. So though the partial measurement induced error improved this particular branch, it actually comes with a larger cost to the performance of other branches and ultimately drop the performance if we use the asymptotic bound to evaluate, as you see in the previous slide. So in summary, we made a proof of principle demonstration of the interactive protocol for quantum advantage. Such demonstration at scale which require about 2,000 qubits by estimation can conclusively demonstrate quantum advantage. Such protocol can also be used between geographically separated parties to serve as a loophole-free remote benchmark of quantum cloud service. The protocol can also be used for certifiable random number generation and remote state preparation. And experimentally, you see that the mid-circuit measurement capability demonstrated here is also crucial for other important applications like quantum error correction. And with that, I would like to conclude my presentation. And again, thanks for the friends and collaborators that all contributed to this great work. Thanks, everyone.
Thanks a lot, Daiwei. That's a really impressive experiment. I should add that Daiwei was the principal architect of this experiment. So yeah, thanks very much. Are there any quick questions before we move to the panel? I guess at this point you can have questions for both either Daiwei or Andru. Oh, there's a question in the Q&A which says, did you come up with the 2,000 qubit figure?
Right, maybe I could answer that. There's this website called LWE Challenge, and there they have a list of some of these very large instances of LWE that were solved, and also the ones that are unsolved. So what we did was we took the smallest instance that was unsolved, and we just plugged in the parameters into that qubit count that I showed for the LWE case. So like the matrix dimensions, the field size, etc. And you could do a similar thing for factoring. I guess for factoring, it's even easier to estimate because there are these industry standards for, say, RSA in how long the key should be, in how long, sorry, the public key should be. And there you would need maybe like 2048 bits, for instance, or something along those lines. So I hope that answers the question.
So if there are no more questions, Daiwei, if you stop sharing, then maybe we can pin up the videos of the panelists. Okay, so let me just start introducing the panelists as their videos are highlighted. So, so it's a great panel today. So we have Chris Monroe, who